This is Bob Capetta from the University of Illinois at Chicago, and this lesson is on Gaussian elimination with back substitution for 2x2 matrices. We have a system of equations, two equations and two unknowns, and our goal is going to be to solve for x and y. Now we have several other strategies to use. We could eliminate variables, we could solve by substitution, we could use matrix inverses, we could even use graphing. This is one more tool that's very effective for larger systems, but let's start with just a system of two equations. So we're going to construct an augmented matrix by using the coefficients. So 1, 3, 1, -1 up top, 4, -5, 13 on the bottom. So our goal is to get a 1 in the upper left-hand corner. That's already there, that's good. Then we're going to use that 1 to turn this 4 underneath it into a 0. And I'll do that as follows. By recognizing that the new row 2 will be -4 times the old row 1 plus row 2. -4 times 1 is -4, plus 4 is 0. That'll get us the 0 underneath the 1s. That's our goal. Now -4 times row 1, -4 times 1 is -4. -4 times 3 is -12. -4 times -1 is +4. We're going to add that to row 2 for -5, 13. -4 plus 4 is 0 as we want. -12 plus -5 is -17. 4 plus 13 is 17. So this becomes my new row 2. I rewrite this matrix. First row is the same. Second row is changed. So 1 in the first slot, 0 underneath that. Then I want a 1 in this corner. So we're going to take the second row and divide it by -17, or multiply the second row by -1/17. If I do that, -17 divided by -17 is 1. We want that. +17 divided by -17 is -1. So my new row 2 is 0, 1, -1. And we could continue. We could use this 1 to turn that 3 into a 0, but the algorithm is more efficient if you use the technique of back substitution. So I'm going to choose not to do that. I'm going to go ahead and rewrite this as x plus 3y is -1, 0x plus 1y is -1, or y is -1, and then we'll solve for x and y. So there are the two equations, and all I've got to do is plug the -1 in for y in the first equation. So we get x plus 3 times -1 is -1, x minus 3 is -1, adding 3 to both sides, x is 3 minus 1, or x is 2. So we believe the answer is x is 2, y is -1, and we write it this way. And it's a good idea to check if it's relatively simple. X is 2, y is -1, 2 plus 3 times -1, 2 minus 3 is -1, checks in the first equation. 4 times 2 is 8, -5 times -1 is +5, 8 plus 5 is 13, checks in the second equation. So we're fairly sure that our work is correct for our first problem. Now this one was fairly simple. They can get complicated when fractions are involved. So let's go through one of those examples. 2x plus 5y is 9. 3x minus 4y is 1. We start by constructing the augmented matrix by looking at the coefficients. 2, 5, 9 up top, 3, -4, 1 on the bottom, written that way. I need a 1 in the upper left-hand corner. The simplest way to do that is to take the first row, multiply it by 1/2, or divide it by 2. 2 divided by 2 is 1, 5 divided by 2 is 5/2, 9 divided by 2 is 9/2. So you'll see what I have there again. Row 1 is row 1 divided by 2, and there is the resulting row 1. So this now is my augmented matrix, but I have to use this 1 to turn that 3 into a 0. So I'm going to multiply the first row by -3 and add that to row 2. So the new row 2 will be -3 times row 1 plus row 2. Now what is -3 times row 1? -3, -15/2, -27/2. And I have to add that to 3, -4, 1. -3 and 3 is 0. -15/2 added to -4. -4 is -8/2. So -15/2 and -8/2 is -23/2. -27/2 plus 1 is 2/2. Negative 27 halves plus 2 halves would be negative 25 halves. This now becomes my second row. We have a 1 in the top slot, 0 underneath that. Then we want to turn this into a 1. Well, to do that, I have to multiply that row by negative 2 23rds. Multiply it by the reciprocal of this number. So my new row 2 will be negative 2 23rds times the old row 2. So negative 2 23rds times negative 23 over 2 will just give me 1 in this slot. Negative times negative is positive, so negative 25 halves times negative 2 23rds is a positive number. The 2's divide out, and I just get 25 23rds. So that equation is 0x plus 1y is 25 thirds. We know what y is. It's an ugly fraction. We're going to go ahead and substitute to find out what x is. So rewriting our matrix now in final form, 1, 0, 1. That final matrix looks like this. And each one of these rows represents an equation. X plus 5 halves y is 9 halves. 0x plus 1y is 25 thirds. So of course y is 25 thirds, and then I have to plug in the 25 23rds, into the y value here to solve for x. So x plus 5 halves times 25 23rds is 9 halves, and yes, indeed, this is a very ugly fraction problem. 25 times 5, 125. 2 times 23 is 46. So x plus 125, 46 is 9 halves. Subtract 125, 46 from both sides, which again, another very unpleasant problem. And what are you going to get? You're going to get x is 41 23rds. It's been a little harder to check, obviously, but if you had a calculator, it would be relatively easy to take 2 times 41 23rds plus 5 times 25 23rds, and you would see that the result is 9, and 3 times 41 23rds minus 4 times 25 23rds would be 1. So indeed, it does check. All right, let's take a look at another question. Oh, writing the answer that way is what we prefer. So writing it in ordered pair form and in set notation to say that is the complete set of solutions. So here's our next question. 5x plus 2y is negative 3, and x minus 4y is 17. If we construct our matrix, we see this. And we want a 1 in this top slot. So you may think, multiply the first row by 1/5, or say row 1 is the old row 1 divided by 5. But that will introduce fractions. We saw how unpleasant they were in the last problem. I suggest it makes more sense to just switch the first and second row. I mean, there's no reason why this row has to be the second row. The second equation could be rewritten as the first equation. And then I have a 1 in the upper left-hand corner. So that'll be my suggestion. Switch first row and second row. And now we have our 1 in the upper left-hand corner, and we don't have any fractions. So that has an advantage. We use this 1 to turn this 5 into a 0. So we'll say row 2 is negative 5, row 1 plus row 2. Negative 5 times row 1, negative 5, positive 20, negative 85. Add that to row 2, 5, 2, negative 3. Negative 5 and 5 is 0. 20 and 2 is 22. Negative 85 and negative 3 is negative 88. And to get into our finished form, we will turn the negative 22 into a 1. So we'll take the old row 2 and divide by 22. Or if you prefer, you could take 1 over 22 times the old row 2. And I have a typo there that I need to fix. So the new row 2 is the old row 2 divided by positive 22. 22 divided by 22 is 1. Negative 88 divided by 22 is negative 4. So my new row 2 is 0, 1, negative 4. So that gives us our final matrix. First row 1, negative 4, 17, and then 0, 1, negative 4. Now you could use this 1 to turn that negative 4 into a 0. But again, if you're solving 3 by 3 or 4 by 4 systems, that is not really an efficient algorithm. So I prefer the back substitution method. So each one of these is an equation. First equation is x minus 4y is 17. Second equation is y equals negative 4. So we're going to go ahead and plug that y equals negative 4 into the first equation. So x minus 4 times negative 4 is 17 is what we'll see next. Of course, negative 4 times negative 4 is positive 16. So we get x plus 16 is 17, and x is 1. Let's check this, because this one's relatively easy to check. 5 times 1 is 5. 2 times negative 4 is negative 8. 5 plus negative 8 is negative 3. Check. 1 is 1. Minus 4 times minus 4 would be plus 16. 1 plus 16 is 17. Check. So we'll write our answer this way. In set form, we have one solution, the point 1, negative 4, and that is our solution set. Our next example is x plus 4y is negative 5, and 3x plus 12y is 1. We always start by writing this as an augmented matrix. Looking at the coefficients, 1, 4, negative 5, 3, 12, 1. We want a 1 in the upper left-hand corner. If we have to divide, we do that, but we have a 1, so that's great. We will use that 1 to turn that 3 into a 0. So we'll say row 2 is negative 3, row 1 plus row 2. What is negative 3 times row 1? Negative 3, negative 12, positive 15. Added to 3, 12, 1. Well, what do we get? Negative 3 and 3 is 0. Negative 12 and 12 is 0. 15 and 1 is 16. So this becomes our matrix. Now we have to think about what this means. First equation is still the same. X plus 4y is negative 5. Second equation is 0x plus 0y equals 16. We like a 1 in this slot, but that's impossible. We don't have one. There's no way for us to get one. But if we have 0x plus 0y is 16, that means 0 equals 16? That's ridiculous. So if you have a situation like that, where you have an untrue statement, all you can say is, there's no solution. So what we have here is we have two lines. The two lines are parallel. They never intersect. There is no point in common for both of those equations. And we have one more problem to look at. X minus 5y is negative 4, and 2x minus 10y is negative 8. First, rewrite as an augmented matrix. 1, negative 5, negative 4, 2, negative 10, negative 8. Again, I'm happy there's a 1 in this slot. We need a 1 in the upper left-hand corner. Make this a 1, make this a 0, make this a 1. That's our usual strategy. I have to turn the 2 into a 0. So row 2 will be negative 2, row 1 plus row 2. So negative 2 times row 1 will be negative 2, 10, 8. I add that to 2, negative 10, negative 8. And you'll notice we get 0, 0, 0. Our usual strategy is 1 in the upper left, 0 here, and then a 1 here. But again, I have a 0 there, and there's no way for me to get a 1 there. So I need to think about what this means. First equation means x minus 5y is negative 4. Second equation is 0x plus 0y is 0. But 0 equals 0 is a true statement. So from a geometric perspective, these are two lines that are exactly the same. So what values x and y are true for both equations? A whole bunch of them. And we want to figure out a way to describe what that set of solutions looks like. You could say infinitely many solutions, and that's correct, but I want a little bit more precise answer here. So I'm going to let y equal t, a parameter. So if y equals t, what is x going to be? We're going to plug the t in for y and then solve for x. So if y is t, then we have x minus 5t is negative 4, and x is negative 4 plus 5t. So we have now written our solution set in parametric form. It looks like this. And I'm just interested in knowing what are some of the elements of that solution set. So I'm going to choose various values for t and find out what x and y are. So if t is 0, x is negative 4 plus 5 times 0, x is negative 4, and y is 0. If t is 1, y is 1, of course. What is x? Negative 4 plus 5 times 1, negative 4 plus 5 would be 1. So we have the point 1, 1 also on that solution set. And let's just do one more. What about if y is 2? So if t is 2, x is negative 4 plus 5 times 2, 10 minus 4 is 6. So we have 3 points, negative 4, 0, 1, 1, 6, 2 in our solution set, but the actual solution set is the set of parametric equations. X of t is negative 4 plus 5t, and y of t is t. And that will conclude this lesson.